Oh, thank you. Hello. Today, we're going to learn three things. Number one, we're going to talk about conditional and absolute convergence of alternating series. And I'm just going to tell you right at the outset that for some reason we like to make a distinction between an alternating series that converges but whose non-alternating cousin diverges, and between that and an alternating series that converges whose non-alternating cousin also converges. And so you get absolute convergence when the alternating series converges and his straight cousin converges as well, and you get conditional convergence if the alternating series converges and the non-alternating cousin diverges. So that's going to take 2 minutes because we just like to make that distinction. And then we're going to learn the error in alternating series. And again, that's going to be really quick because there's no figuring to be done. The error, maximum possible error in an alternating series, it is just the first neglected term. It's that simple, you know? And then finally, the ratio test, okay? The ratio test is the last test we have for testing convergence and divergence of series. And it turns out the ratio test, here's my notes for our lessons, and the ratio test takes up that much space. So the ratio test is incredibly easy to teach, you know? So that's what we're gonna do. Let's get it on, okay? First, conditional and absolute convergence, okay? Conditional. Conditional convergence. Okay, you get conditional convergence if if the sum as n goes from whatever, from 0 to infinity or 1 to infinity, it doesn't matter which, if the sum of the alternating series converges, but the sum of the non-alternating series diverges. A positive cousin diverges. Then you get conditional convergence. You get absolute convergence if the alternating series converges and the non-alternating series, the positive cousin, converges also. Okay, let me ask you this before I start giving you some examples. Could there ever be a situation where the alternating series diverges, but the positive cousin converges? Could that ever happen?
Yes. Somehow.
Okay, well, if the alternating series diverges, then think of the second criterion. What does the second criterion say about the positive series?
Is it 0? Or is it equal to 0 as the limit approaches infinity?
Okay, good. That's the second criterion for alternating series converging is I need the infinitieth term to equal 0. But suppose I've got a alternating series that diverges. Then this guy is violated, right? So what does that say about my non-alternating series, my positive series? If the infinitieth term is not 0, then would my positive series converge or diverge?
Diverge.
Yeah, by which test?
The nth, right?
Yeah, the nth term test for divergence. And I want to get you used to thinking about that, the fact that alternating series converge easier, more easily than positive series, than its non-alternating cousin. right? Remember when I showed you the geometric where if I just added up the terms, I got 6, but if I turned it into an alternating series, I got something way smaller? Do you remember when I showed you that? And so I want you to get used to the fact that alternating series converge more easily, which means if the alternating series diverges, then guaranteed the positive cousin's going to diverge, because the positive cousin's always going to be bigger than the alternating series. You see it? And also because of the nth term test for divergence. If your alternating series diverges, then there's no way your positive series is going to converge. So I just want you to see that if the alternating series diverges, so must the positive cousin. Okay. So let's go ahead and do some problems. Here. The sum, here's example number 1. The sum as n goes from 2 to infinity of -1 to the n power over the log natural of n. Okay? Let's have a quick vote. Does this alternating series converge? Does the alternating series converge? And remember, you want to ask yourself, number 1, remember, you're looking only at the positive cousin. So you're only looking at 1 over log natural of n. You're not looking at the alternatingness of it. Are the terms decreasing? And is the infinitieth term of the non-alternating cousin equal to 0? Please think about that for a second, then we'll make our determination. Okay, tell me, does this guy converge? Does the alternating series converge?
Yeah, yes.
Yeah, good for you. Both criteria are satisfied. The terms are getting smaller and smaller, and the infinity term is 0. Good. Now, let's look at whether the non-alternating cousin himself converges or diverges. Hey, that guy, does that guy converge or diverge? Hey, let's have a vote. How many people say 1 over log natural of n converges? How many people say 1 over log natural of n diverges? Okay. Amber, how did you know it diverged? You're right.
Because ln of n is 1 over n, so the n goes to the numerator and the numerator just increases.
Okay, but you're thinking in terms of derivatives. But here you just want to look at 1 over log natural of n. You just stick with log natural of n. But there's another reason why I know. Yeah, Carly?
Because the log natural of infinity is infinity.
Okay, alrighty. But the log natural of infinity, being infinity, would argue the infinitieth term is 0, and that would argue for convergence. But it turns out this guy diverges. So now, has anyone figured out why? How do I know this guy diverges? Is there a series we can compare it to?
1 over n.
1 over n? Okay, let's compare it to 1 over n, which, by the way, which diverges. Okay?
All the
No,
Okay.
because you don't have an exponent.
Yeah. What's true about log? If I did a term-by-term comparison, what's going to be true about 1 over log natural of n versus 1 over n?
It's going to be less.
Great.
It's great.
Yeah, these guys are bigger than these guys because log natural of n is less than n, right? Do you see that? That when I plug in, the term by term, I'm going to get, this is going to be 1 over log natural of 2 and 1 over log natural of 3 and 1 over log natural of 4, which are all pretty small numbers.
Yeah.
I mean, the denominators are small. This is going to be 1/2, 1/2, 1/3, 1/4. You see what I mean? So these guys are bigger than these guys, and this diverges. You see? And that's because of our little hierarchy. And I'm going to say it over and over again, as as n approaches infinity, the log natural of n is always going to be way, way less than n, which is way, way less than e to the n, which is way, way less than n factorial. That's my hierarchy. And so I've got a situation where in no time at all, n is going to be way bigger than log natural of n, and this guy diverges, which makes then these fractions are going to be bigger, you know? So I hope you see that my positive series diverges. So since my positive series diverges and my alternating series converges, what kind of convergence do I have here? Conditional or absolute?
Conditional.
Yeah, conditionally convergent. Conditionally convergent. Because the alternating series converges and the non-alternating series diverges. Hey, let me give you another one. The sum as n goes from 1 to infinity of negative 1 to the n power over n squared. You're going to ask yourself two questions. Does the alternating series converge or diverge? And does the positive cousin converge or diverge? Please think about that, and then you can decide whether that guy is conditionally or absolutely convergent. I'll give you another minute. How's your table? Oh, I already did. Just the walk was asked. Alrighty, time's up. First, the alternating series. Remember, what do I look at to determine if an alternating series converges or diverges? And I've, established that it is an alternating series. Then what do I look at to make that determination? Do I look at the alternating terms? Do I go, okay, -1 minus plus a fourth minus a ninth plus a 16th? Do I look at the alternating series, or do I look only at the positive cousin? Yeah, only look at the positive cousin to determine whether your alternating series converges or diverges. So I'm only looking at 1 over n squared. Okay, that's all I'm looking at now. I don't care about the plus and minus when determining whether the alternating series converges. And I just need to ask two questions. Are the terms decreasing? And is the infinitieth term of the positive cousin equal to 0? Well, you tell me, how many people say both of these are satisfied and the alternating series converges? Okay, yay. Okay, so this gets to be a big yes. How about the positive cousin? Now we're actually looking at the sum of 1 over n squared. Does that guy converge or diverge?
Converge.
How many people say it converges? Okay, how'd you know?
P series.
Yeah, P series where P is greater than 1. Good, good for you. So tell me, is this, what do you call it? Conditional or absolute convergence?
Absolute.
Good, great for you guys, great for me. Absolute convergence. Okay? Hey, let me give you one more. Here comes another one. The sum as n goes from... I got a good one here. Yeah. N goes from 1 to infinity of -1 to the n power times n over 2n minus 1. I'd like everyone to please tell me, how does this converge? Is it conditional? Is it absolute? Does it diverge? Please make that determination now. Okay, what'd you guys get?
Diverge.
How many people say diverge? Good for you guys. How'd you know it diverged? Who wants to tell me? How'd you know? Yes, go ahead, Chris.
Because if you plug in infinity, you get 1/2 instead of 0.
Beautiful, beautiful. The limit as n approaches infinity of the positive cousin is not 0. Yeah, so it diverges. Well, the alternating series diverges. Does that mean that the positive cousin diverges guaranteed?
Yes.
Absolutely. Oh, yes. Yes.
Can you do the questions out of order? 'Cause
Sure.
It's easier to tell with the limit rather than just doing the increasing.
Yeah, fine. Yeah. Andrew's going, hey, can I do this first and that second? And the answer is absolutely. Sure. Yeah. And frankly, I can't think of any alternating series where this would be a yes and that would be a no. So usually if it doesn't converge, this guy's the no. He's the culprit, you know? So yeah, I think you're probably smart to do that first. Yeah. Okay, great. Hey, here's the last one. The classic term. I give you 30 seconds, okay? -1 to the n power over n. Is that conditionally convergent, absolutely convergent, or does it diverge? I give you 30 seconds. Okay, here we go. Time's up. How many people say this absolutely converges? Converges absolutely. Okay, one of you, one brave soul. How many people say it conditionally converges? Okay, how many people say it diverges? Okay, good. Someone explain. You're correct. This is the classic conditionally convergent series. This is it. This is the end all and be all. Why? How'd you know it conditionally converges? Yes, Kylie.
Because it decreases and it's equal to 0, so you know the first part converges, but
Yes.
the positive or the positive one is divergent.
Yeah, beautiful. 1 over n diverges. Great. Okay, hey, that's it. Go ahead.
So unlike an AP test, would they ask, okay, so this alternating series converges, what would they call the other one? Because I don't think they'll call it its positive cousin on the AP test. Do you know what they'll call it on the AP test?
I don't know. I don't remember there ever being a problem where they referred. You know, at most they would talk about -1 a sub n and then a sub n. They would talk about, -1 to the n power. They would talk about that.
Oh, okay.
They don't have English words for it. They would just use symbols,
Oh.
you know. So in your own mind, you're going to say, you know, this guy and that guy.
All right.
Yeah, good question. Okay, it's time to do the error in the alternating series, and I don't think we're going to get to ratio test, and that's okay, because ratio test is so huge. And I don't know, I mean, we're like 10 days ahead of last year, so we're doing pretty good.
Wait, really?
Yeah,
Oh.
yeah, we're learning, tomorrow we learn ratio test, and tomorrow is day 23. And last year, we learned a ratio test on day 30. So we're actually 7. We're 7 days ahead of last year's schedule. So, you know, you guys are awesome. We're gonna have a lot of time to prepare for that AP exam. A lot of extra credit. Okay. The error in alternating series. I'll just tell you right now, the error in the alternating series is the first neglected term. That's it. That's your maximum, and I should say maximum error in an alternating series is the first neglected term. Let me give you an example. Suppose I say the cosine of x is approximately equal to, let me see, that's an even, cosine is an even function, so I need all my even terms. Okay? And I say, okay, I want to get the cosine of x, and I'm going to use that fourth order, actually it's fifth order, approximation to approximate cosine of x. But you'll notice this is an alternating series, correct? And in fact, I'm just going to keep going. Okay? So cosine of x is actually equal to this infinite series that alternates. And so now I'm going to make an approximation. I'm going to say the cosine of x is approximately equal to 1 minus x squared over 2 factorial. And so I'm going to get an expression for the cosine of 0.5. Okay? This is centered at 0, right? This is my approximation centered at 0. So I'm going to get an approximation for the cosine of 0.5. 0.5 squared over 2 factorial. And that equals, what is that, 1/8? 1/2 over 2, no, 1/4. So I get 0.75. No, that is 1/4. Over 2 is 1/8. So 0.875. Okay, so that's my approximation for the cosine of 0.5. It's about 0.875. What's my maximum possible error? Hey, I'll tell you, the first neglected term, right? The first neglected term. This would have been my next term. This was my first neglected term. It's the first term that I decided not to include in my answer. So this guy's the first neglected term. So the maximum possible error is going to be 0.5 to the 4th power over 4 factorial, which is equal to, oh, I can figure that out, can't I? No, I can't.
0.0625 over.
Yeah, exactly. So I got 0.0026, okay? So that's it, you know? So the cosine of 0.5 is going to be 0.875 plus or minus 0.0026. That's what it is. First neglected term. You guys ready to do one on your own?
Yeah.
Yeah.
Okay, that's what I like to hear. Then go ahead and you know how the sine of x is approximately equal to x minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial minus dot dot dot? Okay, so we're going to make an approximation. The sine of x is approximately equal to this, okay? So now I'd like you to approximate the sine of 0.5 using the 3rd order, even though it's actually a 4th order, approximation, and get maximum possible error. please do this now. And I'll give you a hint, stick 0.5 into that. And then go ahead, your error is going to be the first neglected term. Alrighty. Well, hopefully you stuck 1 in, or I'm sorry, 0.5. So I got the sign of 0.5 equaling 0.5 minus 0.5 to the third power over 3 factorial, which gets me what is that? 0.5 minus 0.5 raised to the third power divided by 6. 0.479. Did you guys get 0.479?
Yeah.
Okay, that's what sine of 0.5 is approximately. So I need to put the little squiggly equal sign to show that it's approximate. And then the maximum possible error. So I'm going to explain to the class, how am I going to find the maximum possible error? Yeah, say it again, Connie. Yeah, first neglected term. I'm going to use this guy, right? I'm going to use that guy, the first neglected term. So the maximum possible error is going to be 0.5 to the 5th power over 5 factorial, which is going to be a pretty darn small number, divided by 5 factorial is 120, right? Whoa. 0.00026. Okay, so, you know, my answer is pretty darn good. You know, that third order approximation is a pretty good approximation. Okay, so now let me have you do one more problem, and then I'll declare us done. And we're not going to do ratio test, and I'm going to have to change your homework just a little bit. I'm going to take off the section 10.7 guys and add a couple of section 10.6 guys. And we'll do ratio test tomorrow. Okay, great. Here we go. I've got a function, but my function is an infinite series. It's the sum as n goes from 1 to infinity of negative 1 to the n plus 1 power over n squared. Okay? And I want you to approximate the sum of this series accurate to within 0.01 of the actual value. If the bell rings, don't go. I'm so sorry, I ended up. Approximate the sum of this series accurate to within 0.01 of the actual value. This is like tonight's problems. This is like problems number 39 through 43. Okay? And let me tell you how you're going to do this. You're actually just going to write out the terms. There's nothing more complicated than that. You're just going to go, okay, when n is 1, I get 1. When n is 2, I get negative 1/4. When n is 3, I get 1/9, negative 1/16, 1/25, minus 1/36, plus 1/49. Let me ask you guys, I'm sorry to keep you, when do I stop?
Whenever you want to.
No, I need to be accurate to within 1/100th of the actual value. Whoops, minus 1/64, plus 1 over 81 minus 100. When do I stop?
All
Yeah, right there, okay? If I stop there, if I make this my first neglected term, okay? And this is how you're going to do 39 through 43. If I make this the first neglected term, all I need to do is add up all of these guys. Add them up. You add up those first 9 terms, you will get the sum accurate to within 100th. How do I know it's accurate to within 100th? Because 100th is my first neglected term. So you, on those problems, you're just going to write it out and keep going until you get your first neglected term to be within what they want the error to be. Okay, and so let me get rid of that. And